What if the most powerful ships of the 1800s moved forward, not with advanced propellers, but with giant spinning wheels? It sounds primitive, but it saved early steam travel. Hidden physics, weak metals, and violent water forces shaped this choice. Stay with us to uncover the truth, and don't forget to subscribe for more fascinating stories.
Welcome to the channel. You are watching Wonders of Innovation.
The early 19th century looked like a revolution on water. Giant steam engines roared. Pistons pumped up and down. Ships no longer depended only on wind. It felt like humans had finally conquered the sea. But something strange happened. When engineers first tried to push ships forward using underwater propellers, what we now call screw propellers, the results were disappointing. Instead of smooth motion, the water around the blades started to behave violently. The problem was something we now call cavitation. At high speeds, early propellers created tiny vacuum bubbles in the water. These bubbles formed when pressure dropped suddenly around rough, uneven blade surfaces. Then, just as quickly, the bubbles collapsed. And when they collapsed, they did damage. Each collapse released tiny shockwaves, like microscopic explosions. Over time, these repeated impacts eroded metal surfaces. Early propellers became pitted, rough, and weaker after only short use. Now imagine this happening on a ship in the 1820s. Metallurgy was still primitive. Iron casting was inconsistent. Surfaces were not smooth. Engineers could not yet shape blades with precision. So instead of solving the problem, propellers made it worse. Ships vibrated. Efficiency dropped. Power was wasted. In some cases, more than 30 to 40% of engine energy was lost due to turbulence and cavitation effects. For early engineers, this was not just inefficient, it was dangerous. So they turned to something simpler. The paddle wheel. At first glance, paddle wheels looked crude. Large wooden wheels, mounted on the sides of ships, dipping into water and slapping it backward. It seemed almost primitive compared to a sleek underwater propeller. But here's the key difference. Paddle wheels operated at the surface, not deep underwater. This avoided extreme pressure changes. No sudden vacuum zones. No collapsing bubbles. No hidden destruction. Instead of slicing through water, paddle wheels pushed it slowly, rhythmically, and predictably. Think of it like walking through shallow water versus diving deep into the ocean. Near the surface, forces are gentler and easier to control. For early engineers, this mattered more than elegance. They needed reliability. A paddle wheel could be built from wood. It could tolerate rough construction. And most importantly, it would not destroy itself after a few journeys. So despite the visual appeal of propellers, engineers realized something important. The technology simply wasn't ready yet. The paddle wheel wasn't chosen because it was better in theory. It was chosen because it actually worked in reality. This moment marks one of the most important turning points in marine engineering. Because sometimes, progress doesn't come from the most advanced idea. It comes from the one that survives. And in the early age of steamships, survival meant embracing the slow, churning rhythm of the paddle wheel.
Early engineers faced a hidden problem. Cavitation destroyed weak materials. Even though propellers looked advanced, they failed in real conditions. Paddle wheels worked because they avoided extreme pressure changes. This shows a key lesson in engineering. Technology must match material limits. A simpler design can succeed where a complex one fails.
To understand why paddle wheels worked so well, we need to look closely at how they interacted with water. At the heart of the system was a simple idea: displacement. Each paddle blade entered the water at a specific angle. Not flat. Not vertical. But slightly tilted, what engineers today would call an angle of attack. This angle was critical. As the blade dipped into the water, it didn't just push backward randomly. It redirected water in a controlled way. The force pushed water behind the ship, and by Newton's third law, the ship moved forward. But here's where things get interesting. Early engineers discovered something called the slip ratio. Slip ratio measures how much energy is lost between the motion of the paddle and the actual movement of the ship. In simple terms, it tells us how much the wheel is slipping in the water instead of pushing effectively. For paddle wheels, the slip ratio was surprisingly manageable, often around 15 to 25% under good conditions. That means up to 75 to 85% of motion translated into forward thrust. For early technology, this was extremely efficient. Why? Because paddle wheels moved slowly. Unlike propellers, which require high-speed rotation to generate thrust, paddle wheels relied on large diameter and low speed. A typical paddle wheel could be over 6 to 10 meters in diameter, turning at just 10 to 20 revolutions per minute, RPM. This slow motion had a huge advantage. It reduced turbulence. Water had time to move smoothly around each blade. There were fewer chaotic flows, fewer energy losses, and almost no cavitation. Even more important, this matched the capabilities of early steam engines. Primitive boilers could not produce steady high-speed power. Instead, they delivered slow, rhythmic bursts of energy. And paddle wheels were perfect for this. Each stroke of the engine translated directly into a push against the water. No need for complex gearing. No need for high precision. Just a steady, predictable cycle. Dip, push, lift, repeat. This rhythm created a kind of mechanical harmony between engine and ocean. It also made control easier. Captains could adjust speed gradually. The ship responded smoothly, not violently. This was especially important for river navigation, where precision mattered more than speed. In fact, paddle steamers became dominant on rivers like the Mississippi because of this exact advantage. So while propellers promised speed, paddle wheels delivered control, stability, and reliability. And in the early 1800s, that combination was far more valuable. Because before you can go fast, you first need to move at all.
Paddle wheels succeeded because of controlled motion and low speed. Their large size reduced energy loss and matched early steam engines. The slip ratio remained manageable, making them efficient for their time. This proves that good engineering is about balance, matching power, motion, and environment rather than chasing maximum speed or complexity.
To truly understand why paddle wheels dominated early steamships, we must look beyond water and into the limits of materials. The 19th century was an age of invention, but it was also an age of imperfection. Iron was widely used, but it was not the strong, uniform material we know today. Casting methods were inconsistent. Air bubbles formed inside metal. Surfaces were rough. Weak points were common. Now imagine building a high-speed rotating propeller from this. A screw propeller needs precision. Its blades must be smooth, balanced, and carefully curved. Even small defects can cause vibration, energy loss, or failure. But early metallurgy could not deliver that precision. As a result, propellers often suffered from structural weakness, uneven rotation, rapid wear and tear, increased cavitation damage. In contrast, paddle wheels were much more forgiving. They were large, simple, and often made partly from wood, which was easier to shape and repair. But the real advantage came from physics. Paddle wheels acted like giant levers. Because of their large diameter, sometimes over 30 feet, 9 meters, they could generate strong thrust without needing high rotational speed. This reduced stress on materials. Instead of spinning fast and risking breakage, paddle wheels moved slowly but powerfully. This matched perfectly with the dominant engine of the time, the walking beam steam engine. These engines were not designed for speed. They operated at low RPM, often below 20 cycles per minute, producing steady but limited torque. A small propeller would have required complex gearing to convert this slow motion into high-speed rotation. But gearing systems of that era were unreliable and inefficient. Paddle wheels eliminated this problem. They connected directly to the engine. No complex transmission. No fragile components. Just a direct transfer of motion. This simplicity increased durability and reduced maintenance, two critical factors for long sea voyages. There was also another advantage. If a paddle wheel was damaged, it could often be repaired at sea using basic tools and spare wood. But if a propeller failed? It was underwater. Out of reach. And often impossible to fix without docking. So engineers made a practical choice. They didn't choose the most advanced system. They chose the system that matched their material reality. And that reality favored size, simplicity, and strength over speed and precision. In this way, paddle wheels became more than just a propulsion system. They became a perfect solution to the technological limits of their time.
Material limits shaped every decision. Weak iron and poor casting made precision impossible. So engineers used large, slow systems instead. Paddle wheels reduced stress and avoided complex gears. This highlights how innovation depends on available materials. Technology does not advance alone, it grows only as fast as the material supporting it.
Out on the open ocean, conditions were unpredictable. Waves rose and fell. Winds shifted. Water depths changed constantly. And in this environment, paddle wheels had another surprising advantage. They acted as stabilizers. Mounted on the sides of ships, paddle wheels interacted with surface waves. As one side lifted, the other dipped, helping balance the vessel. This created a kind of natural rhythm with the sea. In contrast, early propellers were fully submerged. Their performance depended heavily on consistent depth. But in rough waters, ships pitched up and down. This caused propellers to operate unevenly, sometimes too deep, sometimes too close to the surface. The result? Erratic thrust. Vibration. Loss of control. For long ocean voyages, this unpredictability was a serious problem. There was also a logistical issue. Imagine something goes wrong. A paddle wheel breaks? Sailors can see it. Reach it. Fix it. A propeller fails? It's underwater. Invisible. Repairing it at sea in the 1800s was nearly impossible. This alone made paddle wheels far more practical. But paddle steamships had one major weakness: fuel consumption. Early steam engines were inefficient. Burning coal to power large paddle wheels required huge amounts of fuel. So engineers developed a hybrid solution. Ships used both sails and paddle wheels. When wind was strong, sails reduced fuel use. When wind failed, steam engines took over. This combination allowed ships to travel longer distances and maintain reliability. However, this balance would not last forever. By the late 19th century, technology began to catch up. Metallurgy improved. Steel became stronger and more uniform. Precision engineering allowed smoother, better-shaped propeller blades, Most importantly, engineers learned how to control cavitation. Curved blade designs reduced pressure drops. Better alloys resisted erosion. At the same time, a new type of engine appeared. The steam turbine. Unlike slow piston engines, turbines could spin at extremely high speeds, thousands of RPM. This made screw propellers far more effective. Suddenly, the advantages shifted. Propellers became faster, more efficient, more compact, better suited for deep ocean travel. And just like that, paddle wheels began to disappear. By the early 20th century, they were largely obsolete in ocean-going ships. But their legacy remains important. Because paddle wheels were never just a temporary solution. They were a bridge. A bridge between raw, imperfect materials and the precise science of fluid dynamics. They represent a time when engineers didn't just chase innovation. They adapted to reality. And in doing so, they kept the world moving forward one slow, powerful rotation at a time.
Paddle wheels offered stability, easy repair, and reliability at sea. But once metallurgy and turbine engines improved, propellers became superior. This shift shows how engineers evolve in stages. Early solutions are not wrong, they are necessary steps. Paddle wheels were a bridge that allowed future, more efficient technologies to emerge and succeed.